The scale is tared with the empty vial placed on the weighing plate. The screw cap is removed during weighing. To prevent spilling lecithin onto the weighing plate, the vial is removed from the weighing plate before each transfer. This process is repeated until the scale displays exactly 0.3 grams. The scale is tared again, this time with the vial containing 0.3 grams of lecithin. 1 gram of castor oil is added using a 30 ml dropper bottle for accurate dosing. We're now going to try mixing the oil and lecithin using a shaker. Inside the vial, the contents are still unmixed. Clear castor oil sits on top of the yellow lecithin powder. The vial is placed into the shaker, and the screw cap is checked to ensure it's properly secured. Then, the shaking begins. It looks like some of the lecithin has started to dissolve into the oil, but the blend still isn't fully homogeneous. That's likely due to the high amount of powder relative to liquid. As the ratio shifts toward more liquid, the lecithin should dissolve more easily. Next, we use a vortex mixer to continue the mixing. Even though the mixture is thick and viscous, the vortex action seems to help. The lecithin powder begins to blend more smoothly into the castor oil, creating a more uniform, homogeneous mixture. The first 3.5 grams of water added to the mixture of 0.30 grams of lecithin and 1 gram of oil resulted in a macroscopic single-phase emulsion. At this stage of the dilution, I added 1.25 grams of water, bringing the total water content to 4.75 grams. The added water was incorporated into the emulsion using a shaker. To keep track, I crossed this amount off the water addition list. Following this addition, the mixture still presented as a stable emulsion. Next, I added 1.50 grams of water, bringing the total water content to 6.25 grams. The emulsion remains stable, however, the vial is now full. No further water can be added without making adjustments. Something must be done before the next addition. To continue the water addition, the contents of the vial were divided into 2 equal portions. The total mass of the emulsion was calculated, and 3.626 gram, representing half, was removed from the original vial. As shown, half of the emulsion was successfully transferred to a second vial. The planned water addition of 1.75 grams was adjusted accordingly, with only half, 0.875 grams, allocated. Approximately 30 minutes after shaking, phase separation was observed. The oil phase had become visible at the top of the solution. As shown here, we're here displaying the A, B, and C weight data, which represents the not yet normalized dilution line for this tutorial. In a ternary diagram, it's essential that the data is normalized, meaning that A plus B plus C must equal exactly 100%. This is required for the plot to make sense. For plotting purposes, only the A and B components are needed. The C value is automatically calculated using the formula. C equals 100 minus A minus B. Before normalization, the data points appear clustered in the C corner of the diagram. This clustering doesn't represent anything meaningful, it simply shows that the data hasn't been normalized yet. The goal of normalization is to convert the raw A, B and C input into a form where the total is exactly 100%. This step is crucial for generating an accurate and meaningful ternary plot. Now, click the Normalize button, then click OK to apply the normalization. Once that's done, you'll see the dilution line clearly. It's displayed as a series of normalized points, stretching from the center right to the lower right of the ternary diagram. To add phase labels to each data point, the phase text must be inserted after the A and B values in the data entry text field. Adding phase information to the points along the dilution line helps clearly identify the one-phase and two-phase regions within the ternary diagram. In this tutorial's dilution line, we can observe that the phase boundary lies somewhere between the last two data points. This marks the transition from a one-phase region to a two-phase region. The dilution line created in this tutorial serves as a starting example, a first step in the process of mapping out phase transition regions in the ternary diagram. However, to fully understand and define the entire diagram, a more comprehensive approach is required. This means you'll need to create multiple dilution lines, not just the single line investigated in this tutorial. So, it's important to make a clear plan for where to place additional dilution lines. By exploring different areas of the diagram, you can build a complete picture of the one-phase and two-phase regions throughout the entire system.
It's just another CHEMIX school tutorial. Thank you for watching. Don't forget to subscribe.